have to reschedule or just get
Well, like obviously last year computer issues are completely different, but I have people who don't even bother to show up or do anything. So that's more of what I'm meaning. Okay.
You gonna record me?
It is recording. Thank you, though, Shane.
Well, I got it.
I appreciate it. Today we are looking at roots and zeros of polynomial functions. I know, sounds fun, right?
Is it easy?
Is it like yesterday, but just like added on?
Kind of.
Well, it's one of yesterday's. There's only 6 questions
on
homework.
There are only, is it 6 or 8? Okay, there's only 6 questions on your homework, so it's not even that long.
Okay.
I did that on purpose so you guys would not be overwhelmed.
I'm already overwhelmed, so it doesn't matter.
Okay, so before we get into the new stuff, I do want to do a review problem where we find zeros and identify like technically the type of zero that it is. So let's say that I have the equation x squared plus 6x plus 9 equals 0. First question, how many zeros do I expect to have? 2. How do you know that? Because the degree of my polynomial is 2, so I expect to have 2. What are we going to use to find these zeros? Do we have to use anything fancy? Could we factor, quadratic formula, what? I can just factor it, right? What 2 numbers multiply together to get 9 and add to get 6? 3 and 3. So this factors into x plus 3 times x plus 3. But those are my factors, and I want to find my zeros. So what do I do with that x plus 3? Set it equal to 0. I have to do that for both of them, technically, because I had 2 zeros. But I get the same answer for each of them, right? So I see that my 0 is x equals negative 3, and this is called a double root because it appears twice. Right. We do not have to repeat them if they're the same number. So that was a pretty easy one. That was a quadratic. We've been doing that a lot. So let's look at one that's maybe a little bit different. For my next example, I would like the function x cubed plus 25x equals 0. How many zeros do I expect to have in the end? 3. Looking at this right now, do I know what types of zeros I'm going to get? Do I know if I'm going to get rational zeros or irrational zeros or imaginary zeros? Yes or no? No, I have no idea. So let's just see what happens. In order to find my zeros here, what's going to be the easiest thing I can do? Math. Do we have a really straightforward route? So why don't I try by taking a common factor out of each of those and seeing if that makes it easier to work with. They each have an x, so I can take an x out of both of them. And I'm left with x squared plus 25 times x.
Now you can do it.
Now I can do what, Bull?
X times x and then 5 times 5.
That would work if that was subtraction.
Oh, man.
But it's not, which means I can use the quadratic formula, or since there's no middle term, I can just set it equal to 0 and solve. Either way, I'm going to come out to the same answers. So what I'm going to do is I'm going to take this x and set it equal to 0. And then I'm going to take this quadratic and set it equal to 0. And I'm going to solve each of those. This one's already solved, x equals 0. This one, however, what would I do to get x by itself?
Subtract the 25 over.
Subtract the 25. And then square root both sides. And I get x equals the positive and negative versions of negative 25. Uh-oh. I put the I out front. I'm so glad you guys know that. Okay. So I get x equals plus or minus I times the square root of 25. Then what's the square root of 25? 5. So I get x equals plus or minus 5i. Anybody confused by that process? We're working on it, so it's okay. How many zeros did I end up with? 3. I had 2 here, and I had 1 here. So all 3 of these need to be listed in my curly brackets when I'm talking about my zeros. I've been doing them for a long time. And they don't always look pretty. Sometimes it looks like my arm just spasmed.
I just do the
You can write them as plus and minus as long as you include those. However, sometimes when we write it as plus and minus, we forget that that's 2 numbers. Okay, so make sure you're recognizing that the plus and the minus indicate 2 different values for our zeros. So I posed a question to you at the beginning of this problem, and I asked, do we know the types of zeros that we're going to get? What was our answer?
No.
So what if there was a way to kind of figure it out?
No.
There is, and it is called Descartes' rule of signs.
That'll probably be
Yeah.
It is Descartes, French. René Descartes was a famous mathematician.
Oh yeah, I got it right.
It's a person. It is named after a person.
Oh. Yeah, so it's not.
No, it is Descartes' rule of signs. If you ever get bored, look up René Descartes. Like, you'll learn a lot of stuff. It's pretty cool.
It's Spanish. I don't know.
Yeah, in Spanish that would be Descartes or whatever. Somebody tells me all the time.
Spanish today
I love that.
because people don't know how to count.
Oh, okay.
Yeah.
I took French in high school, so anytime I can like hear French or anything, it's fun.
Say five Spanish words.
Je m'appelle Brigitte. Comment t'appelles-tu?
That means.
I said my name is, well, my French name was Brigitte, but then I asked what your name was.
I heard 2, so it's like you're asking me.
No, 2 is you.
Yeah.
It's the
yeah.
oh yeah.
Yeah, 2 is
Yeah.
you.
Okay. Some parts of them are yes. Okay, so Descartes' rule of sign has 2 rules. One that applies to the number of positive roots and one that applies to the number of negative roots. When I talk about a positive root, I'm literally talking about a positive number. When I'm talking about a negative root, I'm literally talking about a negative number. Okay? So the first rule says that the number of positive roots for a function f of x is the same as the number of sign changes in the original function. Or if it's not equal to that number of sign changes, then it is less than the number of sign changes by a multiple of 2. That happens. I know it's really, really, really confusing. Write it. When we do some examples, it'll make more sense. So that is the rule for the number of positive real roots. Okay, this only applies to real numbers, so imaginary are not categorized in this. We also have a rule for the number of negative roots. And that is that the number of negative roots of my polynomial is the same as the number of sign changes and my polynomial evaluated at negative x. If it's not equal to that number of sign changes, then it's less than the number of sign changes by a multiple of 2. This is the first half of your homework and it's the first 4 problems.
And that is the paragraph.
No, the examples that will go with the paragraph or paragraphs. Madison, no, you do not have to come to the school to take the final exam. You're supposed to take it in whatever format you are supposed to be in. So if you're virtual, you take it virtual. If you're in school, you take it in school. Although I wish we could make you all come in for it. I will say that.
I wish I could just go. But Floor, he's making his harder this year.
Because there's a lot of cheating happening. Yes.
That's not our fault. But they also don't know what's going on, so they can't really cheat something if they don't know what's
I
going on
know.
at the beginning.
I know. Okay, dokie. Are we all done writing this? Yes? Okay. So let's do some examples. I know we're super thrilled. First example is I would like to state the number of positive, negative, and imaginary zeros possible for the given polynomial.
It was open.
The first polynomial that I would like to look at is f of x equals x to the 6th plus 3x to the 5th minus 4x to the 4th minus 6x cubed plus x squared minus 8x plus 5. You all look so sad.
No, we do
Yeah.
have finals next week.
We're
It's
all
man tests every day.
Yeah,
Really
6
things
tests
to
in a
do.
row.
Math homework always.
I have to grade 6 tests in a row. Does that count?
No, because you just look at it and
You
go,
get paid
right,
for it.
wrong, X fail, you fail. We have
I
to
wish
give
it were
the
that
full
simple.
pass. It is.
Okay.
We have to worry.
Then I will no longer give partial credit to Bolt's test.
Ah.
That seems like that's what that was just telling me.
You have to like do it. Oh,
Yes.
only she likes
curving.
Yeah, just hers.
Just like
The curving.
Oh yeah. No, I give partial credit, I curve, all that fun stuff. It's fun. Whatever. Okay.
Oh yeah, you still have to calculate
Maybe
like
an English
partial
teacher, I feel like would be easier. Maybe.
So as I'm looking at this problem, the first thing I like to do is identify the total number of zeros I need to end up with. What would that be for this problem? 6, because my highest degree is a 6. So I always like to write that over on the side. That will come in handy in a few steps. I always like to identify my number of positive roots possible first, because it deals with the function in its original format, so f of x as is. I just need to count the number of sign changes that are present in that original function. When I talk about a sign change, I mean it goes from a positive term to a negative term or a negative term to a positive term. Okay, so I just go down the list. Is my first term positive or negative?
Yeah.
What about my second term?
Yeah.
What about my third term?
No.
So there was a sign change between my second and third term. Going from the third to the fourth, I went from a negative to a negative, so there's no sign change. Going from the fourth to the fifth, I went from negative to positive, so there is a sign change. Going from the fifth to the sixth, there is a sign change because I go from a positive to a negative. And from the 6th to the 7th, there's also a sign change because it goes from a negative to a positive. So how many sign changes did I have?
4.
4. This means that when I'm calculating my possible number of positive roots, it's 4 or 2 or 0. So whatever number of sign changes I have, I just keep subtracting 2 until I get to 0 or to 1, because those are the lowest values I can go. So I took my number of sign changes and subtracted 2 each time until I got down to 0. Everyone okay with that?
Wait,
Yes.
4 or 2? What's the word 2 or 0?
So I'm not guaranteed to have 4 positive roots. I could have 2 positive roots or I could have 0 positive roots. This is an approximation. Yes, dear.
Have negative is-
We cannot have a negative number, which means we always stop at 1 or 0.
Oh,
Yeah, we always go down to either 1 or 0 depending on what I started with.
what happened to me?
You could have 3 or 1, you could have 5 or 3 or 1, you could have 6 or 4 or 2 or 0 because I had the 4 sign changes. So I start with 4, 4 minus 2 is 2, 2 minus 2 is 0 every single time. That's what I meant by it differs by a multiple of 2. Now I do my negative sign changes. So when I do my negative, I'm not dealing with the original function. I'm dealing with the function evaluated at negative x. So I'm going to break it down really, really far for you the first time so you can see what's happening, and from there we'll just kind of generalize it. So this means everywhere there's an x in this original function, I'm going to put a negative x. Okay? So this becomes negative x to the 6th plus 3 times negative x to the 5th minus 4 times negative x to the 4th minus 6 times negative x cubed plus negative x squared minus 8 times the negative x plus 5. So everywhere there was an x, I put in negative x.
Oh my goodness.
My next step is going to be to simplify this. So that, yes. But that gets really, really complicated when I have a negative x and I'm trying to figure out what negative x to the 4th or 6th or 8th or 9th power is. So I always like to tell kids that we can break negative x up into negative 1 times x. So then negative x to the 6th becomes negative 1 to the 6th times x to the 6th plus 3 times negative 1 to the 5th times x to the 5th minus 4 times negative 1 to the 4th times x to the 4th minus 6 times negative 1 cubed times x cubed plus negative 1 squared times x squared. The negative 8 and the negative x I can put together to be a positive 8x and then plus 5 at the end. So every single one of my negative x's I separated into negative 1 times negative x. So when I take that to a power, I'm taking each of those individually to that exponent. By doing this, all of my x's are now positive, and I only have to evaluate the negative 1 to that power, which makes it a little bit easier to work with. If you're comfortable doing it from here, you can absolutely skip this step. I do this because it seems to help a lot of students. So then once I have this rewritten, I just need to evaluate whether negative 1 to each of these powers goes negative or goes positive. That's all I need to do. So what's going to happen when I take negative 1 to the 6th power? Positive or negative? What do you guys think?
Positive.
Negative 1 to the 6th power. That means negative 1 times 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 negative 1. Positive. Anytime we take a negative to an even power, it's positive. So that means this stays positive x to the 6th. So then what's going to happen to that negative 1 to the 5th power? It's going to be negative. Negative 1 times 3 is a negative 3, and then I tack on the x to the 5th. Then I take negative 1 to the 4th power, which is positive. Positive 1 times a negative 4 is a negative 4, and I keep the x to the 4th. And I just keep doing this, applying the negative where it stays. So negative 1 cubed is negative 1 times a negative 6 is a positive 6. And the x cubed stays. Negative 1 squared goes positive. Positive 1 times x squared is just x squared. Then I have the plus 8x and the plus 5. I was just evaluating whether my signs would go positive or negative on each of the terms based off of the exponent that I applied to the negative 1 value. So negative 1 to the 6th was positive, so my first term was positive. Negative 1 to the 5th was negative. Negative times a positive makes a negative, so my second term was negative. Negative 1 to the 4th was positive. Times a negative is a negative, so my third term is negative. I just keep evaluating this as I move through the list. There is a shortcut to this, however, that sometimes makes it a little bit easier. Any term with an even exponent keeps its original sign. Any term with an odd exponent changes signs. So if we notice, my x to the 6th stayed the same. My x to the 5th changed from a positive to a negative. X to the 4th stayed the same. X cubed went from a negative to a positive. Oh. X squared stayed the same. Negative x, which is degree 1, went from a negative to a positive, and the 5 stayed the same. So any term with an even exponent stays. Any term with an odd exponent changes signs when I plug in the negative x. Once I get to this step, I go ahead and I count my number of sign changes again. So how many sign changes do I have present here? Well, I have one here, and that's it, right? So that means when I'm counting my negative sign changes, I had 2. So I will have how many negative zeros? 2 or 0. Yes.
Say even stays.
Even sign stays the same. Odd sign changes. Even powers stay the same. Odd sign changes. Every single time that'll work. So now's the really, really fun part that comes with Descartes' rule of signs. We're going to do a sign table. This is still the same example. They don't always take this long. We're just doing it really, really slowly and breaking it down really far. So I always start with my positive. Then under that, I'll do my negative. I need to have a row for imaginary. And then I'm going to tally at the bottom. Okay, so just set your table up like this. Okay, are we ready? We're going to start by listing the positive possibilities that I had. So how many possible positive roots could I have? Everybody look at the example. How many possible positive roots could I have? 4 or 2 or 0. Right there. So that means next to positive, I'm going to write 4 or 2 or 0. I would suggest writing fairly small because we're going to be adding on to the right-hand side of this table. We sometimes have to repeat that list of possible positive values depending on how many negative possibilities I had. So how many negative possibilities do I have? 2. 2 or 0. So that means this list has to be repeated twice. So I have 4 or 2 or 0, and I repeat that, 4 or 2 or 0, because I'm going to be testing each one of these at each of my negative possibilities. So the number of negative tells me how many times I repeat my positive list. Now all I have to do is fill in my negatives under each of these possibilities. So my first negative possibility was 2. So I'm going to test each of these with 2 negative roots. My other possibility for negative was 0. So I'm going to test my second set with 0 negative roots. And I'm trying to find the combinations that I could possibly have for types of roots. It's rough. I know it's rough. It's very confusing. So each of my positive possibilities gets tested or paired with each of my negative possibilities. Okay? This is the even more fun part. How many roots did I need in total for this polynomial? 6. So I'm actually going to be filling in this imaginary row with however many roots I need to make each column add up to 6. Okay? So if I have 4 positive and 2 negative, how many imaginary roots could I have? How many do I already have? 6. 4 and 2 is already 6. So I have room for 0 imaginary roots there. I have to make each column add up to 6. 4 plus 2 is already a 6. So there's no room for any imaginary. Then I look at my next column. If I have 2 positive and 2 negative, that adds up to 4. So how many imaginary could I have? 2. Because 2 plus 2 plus 2 equals 6. If it helps, you can tally them up at the bottom and make sure that each column adds up to 6. My next one, if I have 0 positive and 2 negative, how many imaginary could I have? 4. Because 4 plus 2 plus 0 equals 6. And I just keep repeating this until all of my columns are filled.
How do you get this, the negative?
The negative row. Okay, so I had 2 sign changes, so I had 2 or 0 negative roots both. So I just took each of these and tested them under one set of my positive roots. So one whole set of my positive, I tested at 2. One whole set of my positive, I tested at 0. Because I had 2 sign changes which correlated to 2 or 0 negative roots. And then that's it. This is our Descartes sign table. So it helps me limit or narrow down my list depending on how many roots I start to find when I do my synthetic division. How do I feel about that? Yes, Sam.
So are you gonna make it equal like 6 on the bottom every single time, no matter what?
We will always make it equal whatever the degree of my polynomial was. So this polynomial was degree 6, which is why I wrote 6 zeros off to the side, because I know each of my columns would have to equal that number. So if I have a degree 4, then I expect each of my columns to be 4.
So which ones are?
We don't know what the real roots are yet. These are the possibilities I could have. Because I have to test each of my positives and each option for my negative. I'm trying to find all the possible combinations of positive and negative I could have. So that's why we repeat our positive sometimes more than one time.
Was that all one?
That was all one question.
Wow.
Okay,
We
where's the
expanded it considerably to slow it down for you guys, and now we'll do the next one and it won't take as long.
Where's the start?
Right there.
Okay.
It felt like a long one.
Is this the first person?
This is the first part of the homework. This is the first 2. Yeah. Or first 4, sorry.
So for the first 4, do we just have to make like a table like that? We don't have to do anything else.
But that's it. Okay, let's do another one and then we'll move on to the second part of the notes. So our next one is going to be the polynomial f of x equals 2x to the 5th plus x to the 4th plus 3x cubed minus 4x squared minus x plus 9. How many zeros will I have in total for this problem? 5. Do I start with my positive or my negative? Positive, because it deals with the polynomial as it was originally written. So for my number of positive roots, I'm just going to count the number of sign changes that are occurring in that original polynomial. Do it on your own first, then we'll come together. You're okay. Reese, how many did you have? How many sign changes? 3. How many of you guys came up with 3 as well?
I can't.
Should have 2. 1 here and 1 here. So I have 2 sign changes, which means I have how many possible positive roots? 2 or 0. Then I'll go ahead and do the same thing with my negative. I'm not going to go through that whole super duper long list like we did before, but I'm going to use that rule we talked about to determine which signs change and which ones stay the same. So any term that has a odd exponent, its sign is going to change. So my first term has an exponent of 5, which is odd. So it's going to go from a positive to a negative. My second term has a 4, which is even, so it's going to stay the same. My third term has an odd, so it's going to change signs from a positive to a negative. My fourth term has an even, so it's going to stay the same. My fifth term is an odd, because there's no exponent there, so we assume it's a 1. So it's going to change from a negative to a positive. And then my constant on the end obviously never changes.
That was a lot easier.
Oh yeah, way easier. But we do it the hard way before we do it the easy way.
I didn't understand the hard way.
That's okay. So now what do we do? Count my sign changes. Negative to positive, positive to negative, negative to positive. So I have 3, correct? Everybody else get 3. Which means I have how many possible negative roots? 3 or 1. So now I'm already ready for my table. So on my table, again, I'm going to have 3 rows. 1 for positive, 1 for negative, 1 for complex.
Or imaginary.
Imaginary, thank you. So I know that for positive, I had 2 or 0. How many times am I going to have to repeat that set? Well, how many negative root possibilities do I have? 2. So I'm going to have to repeat that positive set twice. So I'm going to have 2 or 0, or 2 or 0. Then I fill in under each of those with each of my negative possibilities. So my first set, I'm going to put the 3. My second set, I'm going to put the 1. And then I will fill in the appropriate number of imaginary terms or imaginary roots. How many zeros do I need in total for each of these columns? 5, because that was the degree of my polynomial. So on the first column, if I have 2 positive and 3 negative, how many imaginary could I have? 0, because I have no room. I'm already at 5. If I have 0 positive and 3 negative, how many imaginary? 2, because 3 plus 2 gives me 5. For my third column, I have 2 positive and 1 negative, so I can have 2 imaginary. And on my fourth column, I have 0 positive and 1 negative. 4 imaginary. Each of my columns adds to 5, and I'm finished. Told you the second one goes faster. How do we feel about this one after having done the second example and everything? A little bit better? Okay. So this is really helpful in our next lesson where we start building a huge list of possible rational zeros. This will help us narrow it down a lot better. So I like to do it in steps, kind of building up to that. So there is a second part to this notes. And it's also not difficult. Or once you get the hang of it, it's not difficult. So what we're going to do for the second part, which is the last 2 problems on your homework, is called the complex, or it deals with the complex conjugates theorem.
Use the complex word to come back.
Always. So the complex conjugates theorem tells me that if the complex number a plus bi is a 0 for my polynomial, then its conjugate is also a 0. By conjugate, I mean the same a and b value with the opposite sign in the middle. So we're going to use this to start with the roots of a polynomial and build up what it looks like in its expanded form. So the example I would like to start with says to write a polynomial function of least degree with integer coefficients, the zeros of which include -1 and 5 minus I. So I'm telling you that these are two of the roots or the zeros for my polynomial, and we need to use this coupled with the theorem above to build what my polynomial actually looks like, or what it could look like. So what that means is I need to take each of my zeros and I need to set them equal to 0, or get them so they're set equal to 0 and turn them back into factors, and then multiply my factors out. Is this all of the zeros for my polynomial? No, why not? Okay, first of all, it says includes, which means I'm probably not done. Second of all, do I have a complex 0 here?
Yeah.
5 minus I is complex because the first part is real and the second part has an I. Which means that because this is a root, its conjugate is also a root. The conjugate being 5 plus I. So we just change the sign in the middle. So that means I'm building a polynomial that has 3 zeros. And in the end, it should have a degree of 3. That's how I know that I'm done and I've done it correctly. So what I start with is I take each of these zeros and I set them equal, take x is equal to each of these zeros. And I want to work backwards from everything that we've kind of been doing. So I would like to take these zeros and turn them back into factors. When we turn them back into factors, I take whatever's on the right-hand side and I subtract it over with the x. So for x equals -1, I'm going to have x minus -1 equals 0. For x equals 5 minus I, I'm going to have x minus 5 minus I equals 0. And for x equals 5 plus I, I'm going to have x minus 5 plus I equals 0. I literally take everything on the right-hand side and subtract it over.
You don't flip the sign.
We will in a second. I just showed you how I moved it first.
Oh, okay.
Of course, once we do that, we can simplify it a little bit, make it easier to work with. X minus a negative becomes x plus 1. I can distribute the negative in this one, so I get x minus 5 plus I equals 0. I can distribute the negative in this one, and I get x minus 5 minus I equals 0. So what I'm going to do next is I'm going to take each of these and write them as factors and multiply them together. So when I do that, I get x plus 1 times x minus 5 plus I times x minus 5 minus I. And I'm going to work in groups of 2. Clearly, I'm probably going to want to start with those right 2 factors. Okay, anytime I have 2 that have an I in them, I want to deal with those first. To remind myself that I'm doing that, I'm going to go ahead and bracket around them. So I remember those 2 are grouped together in a special relationship because they're going to build a nice, pretty looking quadratic. And we're just going to FOIL it out. So each of these is going to be multiplied into each of these. So I'm going to draw arrows and I'm going to color code so you can kind of see what's happening, which should make it a little bit easier. So I'm going to start with blue. I'm going to take this x and I'm going to multiply it into each of the terms in that second trinomial. So x times x becomes x squared. X times a negative 5 becomes negative 5x. X times a negative I becomes negative xi. Then I move on to my second value in that first trinomial, which is negative 5. So I get negative 5 times x is negative 5x. Negative 5 times a negative 5 is positive 25. Negative 5 times a negative I is positive 5i. I do the same thing with my third term in that first trinomial, which is I times x is a positive xi. I times negative 5 is negative 5i. I times negative I is negative I squared. And then we combine like terms and simplify. So there's nothing else I can combine with this x squared, so it's gonna drop down. I like to cross these out as I move through them so I don't forget anything. Then I notice I have a negative 5x and a negative 5x, which I can put together to be negative 10x. My next term is a negative xi, which I see is going to cancel out with the positive xi I had closer to the end. Then I have a positive 25, which I can't combine with anything the way it is. My next term is a positive 5i, which will cancel with the negative 5i farther down. And my last one is a negative I squared. Is this simplified all the way?
The negative I squared.
Then I squared becomes negative 1. Negative of a negative 1 makes it positive 1. So I'm going to have 25 plus 1, which is 26. So that super duper ugly imaginary foiling turned into the beautiful quadratic that is x squared minus 10x plus 26. Is this my final answer? No, I still have this x plus 1 that I have to deal with. All I did was I simplified that mess. Which means to finish out this polynomial, I just have to FOIL this out as well. So then I'm going to have x times x squared is x cubed. X times a negative 10x is negative 10x squared. X times 26 is 26x. 1 times x squared is x squared. 1 times negative 10x is negative 10x. And 1 times 26 is 26. And we will combine like terms and simplify. And once I get it simplified, I end up with the beautiful cubic equation that is x cubed minus 9x squared plus 16x plus 26. I am pretty sure that I'm right because I had 3 zeros to start with, and my answer was an x cubed, which means it's degree 3, so I'm good to go.
Would that be the answer?
Yes, this is the polynomial I was looking for. How do we feel about that? Nah, not good. Okay, well, I don't think we have enough time to start another example. So there are actually like 4 more examples in the notes that you can look at, but they all work the exact same way. I would like to point out one thing because I did put it on your homework. If I have the imaginary number that is 5i as a 0, what's the conjugate of 5i? Negative 5i. Okay, so we just changed the sign on the imaginary term. Have an absolutely wonderful day. Thank you.